Hi again. Now that we've laid out all the conditions and our models for our sampling distributions, I wanted to come back and explain two things in more detail. One is the large population condition. The other is the success failure condition. So we'll come back to that one. So the large population condition is needed for means and proportions. So for any sampling distribution and anything that uses a sampling distribution, like when we do confidence intervals and hypothesis tests, using these theoretical methods, we need to check for this, okay? So if we're sampling, just to repeat what it is, if we're sampling without replacement, we must be sampling from a large population to consider the individuals independent of each other. Okay, and sometimes it's also called the 10% condition, or said that the population must be 10 or 20 times our sample size. 10% corresponds to the population is 10 times larger, right? 1/10 or 10%. So that's actually 5% condition. Okay, so I've got more on this on the next page. So I want to talk about this and give you kind of a visual here. So for small and large populations, imagine around Halloween time or whenever, if you ever get one of those small bags of M&Ms. Okay, so if you have one fun-size bag of M&Ms, this tiny bag of M&Ms as your population, if you take one M&M out, what happens to the chance of selecting each color? You know, let's say you've got about this many. This is about like, I don't know, maybe 10 or 12 M&Ms here. I could actually count them. 4, 5, 6, 7, 8, 9, 10, 15. Okay, 15 M&Ms here. And let's say you just want to know what's the chance of a particular color. Well, there's a very small number, right? So if you take one out, it influences the probabilities a lot, right? Okay, so we don't want that because we usually sample without replacement, meaning we wouldn't survey the same person twice, or we wouldn't measure the same tomato plant or the same auto part twice. Okay, so we most often are sampling without replacement. Okay, now let's say you have this giant Costco or industrial size huge box of M&Ms as your population. What if you take one out? It doesn't change it very much, right? It's just by a fraction. It's probably in the 5th or 6th decimal place. Okay, so this is why we need this large population condition. Because if we take one M&M out of our tiny bag, then we would say these M&Ms are no longer independent from each other because the probability changed a lot. Versus if we take one out of the giant box, we could still consider them roughly independent because we've changed it, but it's so small, it's not going to affect our calculation. Okay, so that's why we use this condition. We say as long as we sample less than 10% of the population, we can say that individuals will be independent and meet this condition. Okay, so the 10%, I feel like the large population makes a little more sense to me because it's more the size of the population rather than the size of our sample. So I'm gonna be switching over to this large population instead of 10%, and we'll see how it goes. So some books say that the population should be 10 to 20 times the sample size or more. Okay, so this is the large population condition. We need to be sampling, and not the whole box, right? We need to still have a small sample in relation to our population, okay? So there are other methods for small samples and small populations. So I'm just going to put brackets around this. So again, if you want to learn more, take more statistics classes because there are methods for small samples and small populations, but they're beyond the scope of this course, okay? So I'm just going to make a note over here saying that we need a small sample relative to the size of the population. Okay, sometimes people think, well, we need a large sample, the more the better, right? But it goes back to the pot of soup analogy. If you're making a pot of soup, do you need to eat the whole thing to know if it's good or not? No, you just need one little sample, but it needs to be representative. If you don't get a carrot in your sample and the carrots aren't done, I wouldn't tell you that, right? Or if the potato's not done, or if the meat or tofu's not done. So we don't need a huge sample, we need a representative sample. I was going to write that, but it's not really related to this actual, I think you've got a good handle on that. It's not related to this exact condition. Okay, so that's the large population condition. Now I want to go and talk about the success-failure condition, and I'll remind you that that is only for proportions. So here's our last notes page. The success-failure is analogous to the sample size. For a mean, we do sample size, and for proportion, we do success-failure. And that's because for means, we have a mean and a standard deviation. For success-failure, we have an n and a p, and it depends on both of these, okay? Not just n. Depends on both of these. So I want to show you that. Okay, so for that, we're going to look at the Rossmann chance applet that we've done before. We've actually looked at this a little bit before, but it'll be good to do it again. So the sample size condition for proportions depends on both n and p, rather than just n, okay? So this outlines right here the simulation we're going to do. Let's simulate 2,000 repetitions of size n equals 10 with a 0.5 probability of heads. So I'm going to go over to the Rossmann chance one proportion applet. And if you're at the Rossmann chance page, which you can Google Rossmann chance applet and it'll come right up, it's the first one under statistical inference on the right side, one proportion inference. Okay, remember we've used this one before for coin tosses when we did our Kiki Booba and some of our other proportion inference. So this says we're going to keep the probability heads up 0.5, so it's 50-50. I'll keep the coin, well, we're going to do 2,000, so I probably won't keep the coins. We're going to do 10 tosses and 2,000 repetitions. Let me just do one at a time since it's been a little while. And I'll show you the coins. Remember, so this is like an individual sample of 10 when it's a 50-50. So this time it was 6 and 4. And then 10 more coin tosses. And I'll get rid of the animation, but I'll keep the coins so you can see. And move it up, and I'm going to change this to proportion of heads since we're always using proportions in our class. So let's do it. There's another sample. Okay, so this is a proportion. So this is like a yes/no. Would you support this candidate? And that's around 50-50. Okay, so we can see what our distribution of random samples would look like. Okay, so now I'm going to put in 2,000. So I have around 2,000. Slightly more is fine. Okay, so let's look at what we notice. So our probability of heads is 50-50, right? And look at where the center of our distribution is, right at 0.5. So that's what we saw, is our mean is equal to p, our proportion of success or whatever we're looking for. Okay, now what I want to show you is related to the success-failure condition. So click on show sliders at the bottom. I'm going to hide coins to move this up. Okay, so this is great because they give us a slider for the value of p and the value of n. Okay, so because this 0.5 is right in the center, this started very centered, okay? But let's see what happens if we change p. So move the lower slider to the left. And as I do that, and as you try it too, what's happening to the shape? More of the probability, you can see it's going down the scale, but it's also changing the shape. This is skewed to the right. Very very skewed. And the more it further it goes down, the more skewed it is, right? So remember, our whole basis for the sampling distribution is that we need a normal model. So if we tried to use this with something with a 3.7 chance of success and only a sample size of 10, our normal probabilities would not work. They would not be accurate because we don't have a normal distribution here. Okay, so what we could do is increase our n. So what happens if I increase my sample size? I'll do it kind of slowly. You can see it's going back to more symmetric, isn't it? Is it going to get there? Because 3.5 is pretty tiny. Let's see how far our slider goes. Okay, so I'm at 100. That's the max for our slider. And it's not quite enough, right? So let me multiply n times p and see. I gotta go back to the notes, so I will in just 1 second. 100 times 0.037, I'll show you that on the note. So I'm taking n times p, which is our success failure, one of our success failure conditions. When I multiply that, I get 3.7. So that's not quite high enough. So it's not quite symmetric enough yet. But if I put this down to somewhere around 10, that's looking pretty good, right? Even 11. So then if I go 100 times 0.11, now I'm up past 10. So now that's working, okay? So that's why we need both n and p, because we don't need much sample size if we're right at 0.5, because it's already normal. It's like starting with a normal population, right? So if I start putting my top slider back to 50-50 roughly, we don't need as big of a sample size for that because it was already normal to start with. But then now let me go to a higher chance of probability, so higher success. I put my n back down to around 10 or 13. Now I'm going to move the slider over to the right, and you can see that the probabilities are shifting to the right and it's skewed to the left. So same thing up here. Okay, so when my P, or chance of success, is very high, I have a similar issue where it's really skewed. So in that case, we need a larger n. So let me move n up again. You can see it's still a little skewed. It's getting more and more symmetric, and it's always centered around P, right? So this 0.937 where I have it right now, that's about the center. Okay, let me go as high as I can go, and this is not quite high enough, right? Because this won't quite be 10. So if I do 100 times, well, this is going to be the high one. So I have 0.937, that's fine. Right? But so this is one where I need to do Q, so the complement. So if I do 100 times 1 minus 0.937, so it has to be 10 on both sides. So that's only 6.3. So that's why it does not look quite normal yet. So if I bring this back to about 90 or so, 0.90, there's 898. Okay, you can also just type it in to get the exact value you want. You can see that looks fairly symmetric. Maybe slightly, you can click on normal approximation here. It's maybe slightly still skewed. And if I do my success failure condition, if I do 100 times 0.9, I get 90, but 100 times 1 minus 0.9, that's the Q, or if I do it 100 times 0.10, either way, I get 10. So that's the minimum we would need to show a normal distribution. Okay, so we're going to practice this a lot. I just wanted to show you why, for those of you that like to know why. You might be curious about this binomial here too. There's another model called the binomial model, and I'm just going to mention it. We're not going to calculate probabilities or anything, but you can see it's actually very close to this as well. And the binomial is actually more used for counts. When you're counting, like what's the probability? You have an n and a p, what's the chance of getting 4 or more successes or something like that. So it's very closely related to the binomial, and then the normal also approximates the binomial. They're very, very similar shape. But the binomial is more of a discrete distribution, and it is a discrete distribution, and the normal is a continuous distribution. Okay, well, I hope that helps. Let me just make sure I've covered everything on the notes page here. I might want to write some of this stuff down. So we clicked on I can't say that, show sliders. We moved the slider for success probability. We noticed what happened. And then we moved the slider for n and noticed what happened. And here's a screenshot on the right. Okay, so let me write down a couple of those tests that I did. So when I did 100 times 0.037, I think that was roughly what it is. It's off my calculator now, but that's moving the decimal over twice. So that'd be 3.7. So that was still skewed. And when I did 100 times 0.10, that was 10. And that was normal, the normal shape. Okay, and then same thing with on the higher side. We did 100 times 0.937, and that was 93.7. That's okay, but 100 times 1 minus 0.937, that was 6.3. So this does not meet the condition. That does not mean the success failure condition. Okay, so the reason we need this success failure condition, remember, it's 4 proportions, and it's because the shape, getting our normal curve that we need to calculate probabilities, depends on both n and p. Okay, so you might be wondering, oh my gosh, there's a lot of information. Let's go ahead and apply it in the next video, and you'll see it's going to be no problem. Okay, I'll see you there in the next video.